percent ionization of acetic acid decreases as concentration increases. Maybe I did it wrong, but I tried like checking it, where I set like, the molarity of acetic acid as a variable and then plugged it in as two different values. And what I got was, as the initial molarity decreases, the percent ionization increases.
That's correct.
So is it not the inverse?
Yeah, so the percent ionization of acetic acid increases as yeah, actually I made a mistake there. You're right. The percent ionization increases, the concentration decreases, but I guess I misread my own question. And so this should have been increases or decreases as the concentration increases. That's true. I screwed that up. Sorry. This one's true. So I'll have to fix that. You're right, Colin.
I also have a question. Number 16.
Mm-hmm.
Need for 1 molar NaOH.
16? Okay. Yeah, I'm gonna write this down. Number 8. I need to fix that. Number 16. pH for 1 molar.
Yeah.
So,
Would it be 9 for the effective concentration? Because it's
9 would be quite a big drop.
yeah, I know it's pretty low. 14 is pretty high.
14 is pretty high. However, from about 0 to 14, it's reasonable. When you go beyond 14, then really you have to worry about effective concentration. And so pHs from about 1 molar base to 1 molar acid is okay. The error is not going to be huge. You're right, it's going to be an error, but an error between 14, because that would be the ideal pH, and 9 would be 5 orders of magnitude. That's like, 100,000 times.
Because I realize it's probably closer to 14, but I thought you were trying to test.
But is the concentration like 100,000 times lower because of ion pairing? It's like orders, you would have to think in terms of orders of magnitude there, because these are all power functions, and so it's powers of 10. And so it would be, if there were something like 13 point something, then yes, but 9 would be a bit too drastic for the effects that you're seeing. I mean, let's say the concentration were cut in half, which would be extreme. The pH wouldn't be all that far from 14.
Number 17, I put C, and the Scantron says that the correct answer is B.
Yeah.
You put C and the Scantron says B?
Yeah.
Okay. Number 17. Okay. I'll fix that. Were there others?
Yeah, could you kind of quickly explain 10 and 12?
10 and 12. All right, 10. 10 is problem number 89, I think, in the homework. And so this one, it's hard to tell because it's 10 to the minus 5, but HCN, which I didn't give you the Ka for. And so this was kind of like from experience, because this is borderline. I don't know if you'd have to solve this simultaneously or not, but this one was requiring simultaneous.
Okay.
Number 11, we did this one in class, and so we did this one stepwise. And so the original one thinking was the pH was going to be 8, but that's base. And so it couldn't be 8. And then since HCl is a strong acid, step 1 is not perturbed, regardless of how much additional hydronium is produced in step 2. And so 11 stepwise.
Yeah.
Okay.
What about
12. This one was, you might have put down simultaneous because of the homework. This one, this was also 89A was HCN, 89B was this aniline, which is very weak. I mean, 10 to the minus 10 is very weak,
Yeah.
but the concentration is 0.1 molar. At the concentration of 0.1 molar, then it was pretty high. Did you do the calculation? And so the amount of hydroxide you produce isn't going to be impacted by KW if you did the calculation on this one, but it's just because it has a high initial concentration, whereas if you have this one, the Ka was very small. I forgot to write the Ka here. It was like 10 to the minus 10 also. But this one's very low concentration of a very weak acid. This one is a fairly moderate concentration, 0.1 molar or 0.10 molar of a weak acid. And in this case, it's not necessary.
Yeah, so one of the things that, I was thinking that was kind of throwing me off was, I kind of had this idea that you need to solve it simultaneously if the molarity is kind of lower than 10 to the minus 7,
Mm-hmm.
because then, water would have a significant effect. But then I didn't really know what to think when you have a decent molarity, but then a really low Kb. So is one more significant in terms of telling whether it's going to be simultaneous or not, or is it just not that simple? You kind of need to go a little more in depth.
It's not that simple. It's not that simple. So the thing you could have done here is just done a quick calc for this. This one, the simplifying assumption works no problem. I mean, and then you could see how much hydroxide you have at the end of step 1, and then see if Kw is going to have an impact. And the amount of hydroxide you generate here, actually, let's just do this one here, just side calculation. So just go to the end here. And so this is going to be 0.10 minus x. And this is going to be x and x. We're going to get x squared over 0.10 minus x is equal to 7.4 times 10 to the minus 10. And what we'll do here is we'll just use the SA right off. And so if we use the XA, then x is equal to square root of 7.4 times 10 to the minus 11. Just do that. Skip some steps. So 7.4 times 10 to the minus 11 square root. And So I end up with 2.0 times 10 to the minus 6. So the essay is valid, you know, it's 10 to the minus 1 over 10 to the minus 6 essentially. And so percent change is very, very, very small. And then that gives this. Now you're thinking, okay, times 10 to the minus 6, you know, it's kind of borderline because you think KW can contribute because KW can have a max of 10 to the minus 7, but when there's the common ion effect, it drops it like an order or two magnitude. So if we go down to 10 to the minus 8, it's not really going to have an impact on this. And so we could see with KW, we wanted to, what kind of impact that has. And the problem of this is if there was a simple way to determine, it would be best, but what we end up having to do is just based on experience to see how that changes. So this is going to be X, and then the hydroxide is going to be 2.0 times 10 to the minus 6 plus X. And that's going to, this times that will equal 10 to the minus 14. And so we could try the simplifying assumption here. If we do the SA, then we get X times 2.0 times 10 to the minus 6 equal to 1.0 times 10 to the minus 14. And so I'll take my number, invert that, times 1 times 10 to the minus 14. And I get 369. I get X equals 5.0 times 10 to the minus 9. And then I check, is that okay? And so I'll do the percent. Percent is the change, 5 times 10 to the minus 9 over the initial 2 times 10 to the minus 6 times 100%. So divided by 2 times 10 to the minus 6 times 100% is 0.25%. And so the SA is okay for this step. And so when we do that, we're going to get down here 2.0, this is 6, so 2.005 times 10 to the minus 6 molar hydroxide. So if we calculate the pH without the this step, the thing is, does this change that significantly? So you could argue maybe it does, you know, 2.0 versus 2.05, or maybe it doesn't. So if we do the pH, let's take a look at the pH here. So we'll to calculate the log 2 times 10 to the minus 6. This would be the POH. Actually, look at pH plus 14. 8.30. 1029. Okay, then we'll calculate the pH if we add this here. .30211. So there is a contribution here. It's a small contribution, so in one sense, you know, we added an additional 0.25%, and so it depends. If you think this is significant, then you should solve it simultaneous. If we don't think this is significant, then we just do it stepwise. And arguments can be made for both, so in that case. So this one wasn't so clear cut. The same thing with 13. And so just because of the higher concentration here, at the lower concentration, definitely it has to be solved simultaneous.
Wait, for 13, is that a high concentration?
This is, I mean, 0.1 is, well, it's not high, but it's high for us, because 0.1 is the usual concentration that we've been doing. So this is kind of your normal concentration. That way we don't have to worry about activities and this kind of stuff, but it's fairly high for our calculation. Sometimes it will go higher, 3 molar or higher, but it's high for us. This one was tricky here, so I'm not sure about this. I would have said simultaneous for this, but it turns out because of the common ion effect, even though these are so similar in K values, that in this particular instance it was not necessary. This one was a homework problem also. This one they asked you to solve it both ways. They asked you to do it, well, they asked you just to do step 1 and ignore step 2, and then they asked you to do step 1 and then factor in step 2. Step 2 contributed a significant amount of hydronium, or insignificant amounts of hydronium. And in this case, it was an insignificant amount because of the common ion. So much hydronium was generated in step 1 that step 2 barely contributed any.
Is that why for the next one, 0.1 molar is considered pretty high again, and that's why you have effective concentration?
This one?
Yeah.
Yeah, 0.1 is considered pretty high molar, but this is a weak acid, so the weak acid the pH of 0.1 molar HF is closer to 3, pH 3, because of it being a weak acid.
So do weak acids always?
I'm sorry?
Do weak acids always kind of have effective concentration?
No, this is not effective concentration. Oh, you mean versus stoichiometric concentration?
Yeah.
Those are two different things. The two different things are partial hydrolysis, which is going to cause the concentration to be lower. And so the reason why the main reason why the concentration is not 0.1 molar you're thinking 0.1 molar H3O plus?
Yeah.
The reason it's not 0.1 molar H3O plus is not because of activities.
It's because of the weak acid.
Yeah, and it only partially hydrolyzes water, partially ionizes. And then on top of that, then you're going to have effective concentrations, which could further lower it, depending on how concentrated it is. So 2 factors. Yeah, these ones with the simultaneous, I was thinking about those ones because these ones were really pretty tricky.
Yeah.
But then a lot of people got this bonus, some bonus points for this here. And so if you actually calculated it using the simultaneous method, then this was worth not 3 points, this was worth 5 points. So if you just got it to where it's simultaneous and you set it up, then it was worth 4 points. But very few people actually solve it, the algebra for this. bit of a pain. But some people do. So that's good. So anyway, I'm going to fix the number 8 and number 17. Were there any other questions on this?
So little of it that it's not going to really affect the pH. Because it has to be. Because this is like the definition of molarity. This many moles of HCl per liter of solution. The solution has to be water. It's
All right, for continuing on with chapter 17, I want to talk about diprotic acids next. And we have the first equivalence point. This is diprotic weak acid. And then we'll have our second equivalence point here. And so let's pick a weak acid. Let's diprotic and take a look at what a good acid would be here. This is actually a triprotic acid here, but does it look like a triprotic acid? No. It doesn't, because we would expect 3 equivalence points for this. So the problem is the third equivalence point is never seen in this phosphoric acid. And the reason is we're titrating it with too weak of a base. I mean, the pH that we need is above 13 to see the third equivalence point, and the max pH that we're going to have is pH of 13, I think. With this, yeah, pH of 13. That would be the max. So if we used a more concentrated sodium hydroxide, too weak in the sense that it's not concentrated enough. Sodium hydroxide is a strong base. But if we used a more concentrated sodium hydroxide, maybe let's say 6 molar, then we probably could see the third equivalence point here. But we aren't going to see it. And the other problem is we might not even see the first equivalence point. Why wouldn't we even see the first equivalence point? Well, if the acid is too dilute, let's say you add too much water, the more water you add, the more water-like it is, and the closer the pH is going to go to 7. And so if we over-dilute this weak acid, we won't see this first equivalence point. And so it might look like a monoprotic acid. We might have a triprotic acid that looks like a monoprotic acid because it's overly dilute initially and we aren't using a concentrated enough base at the end. So I'm going to not do phosphoric acid here. We're just going to look at a diprotic acid. Like, let's see, which one would be good. Let's see, the table. I have to go to the appendix. Well, let's just pick one off that table up there. Which one should we do? Sulfurous acid? All right. We'll try sulfurous acid. Now, how many milliliters should we go of the sulfuric acid and what concentrations should we have? So oftentimes in these titrations we pick 25 milliliters or something like that or more. We put it into a Erlenmeyer flask. Do you know the reason why they use Erlenmeyer flasks instead of beakers? Easier to swirl. Beakers are hard to swirl without stuff splashing out, but Erlenmeyer flasks, it's really easy to swirl by hand. If you have a magnetic stirrer, it also helps because if there's any splattering with a magnetic stirrer, it's caught by the walls and drains down the walls. In a normal titration, you rinse the walls off because the splatter is going to contain acid, and you want to make sure all the acid's down here to be titrated. And so you rinse off the walls. But in a pH titration, we don't rinse the walls because that will change the pH. And so in a normal titration, we're continually rinsing the walls down. Rinsing the walls down with DI water is not going to change the number of moles of acid that you have in there. It won't change the number of moles of acid, but it will change the concentration by adding more water, which will in turn change the pH. And so there is a risk that we have splattering here. And what you do with the splattering is you tilt the beaker or you tilt the Erlenmeyer flask to capture the splatter so that we titrate all the acid in there. You know. Anyway, we're going to titrate. Maybe we'll titrate it. We'll just say there's, keep the numbers simple. Maybe we'll try to keep it simple. We're going to use 0.100 molar sodium hydroxide, again, as our titrant. But down here, maybe we'll change it to make it a little bit more complicated. Maybe in this case, we're going to have 0.200 molar sulfurous acid, H2SO3. There's a problem with the sulfurous acid, and so this is one of the things to be aware of. If you look at sulfurous acid on that chart, do you see in parentheses, what does it say? Yeah, it decomposes into sulfur dioxide and water. Now there's going to be an equilibrium between sulfur dioxide, water, and sulfurous acid. And we have to be aware of that. And not only that, we have to worry about solubility. You know, how soluble is sulfur dioxide? And how do we maintain that equilibrium? And so if you were to actually do this titration with sulfurous acid, the best thing is to put a blanket of SO2 over it to try to keep the SO2 from degassing out. And as the SO2 escapes, then that's going to change the concentration of the sulfuric acid inside the flask itself. And so sulfuric acid, it would be a good diprotic acid. However, because of those complications, we probably are not going to do this one. It's the same thing with carbonic. Is it easy to make any molarity of carbonic acid you want in solution? No, that involves bubbling the CO2. Now, how can you control the bubbling of the CO2 in water to effectively change the concentration? And so those are things we have to worry about. CO2 is actually, the equilibrium for CO2 is actually quite interesting because for a while, a lot of people were worried about the pH of the oceans. The pH of the oceans going down because of greenhouse gases like CO2, but then the CO2 is incorporated by marine organisms to build, their exoskeleton, their shells, whatever. And the coral reefs as well. And so there's really a really complicated equilibrium going on in the ocean where there was a decrease in the coral, but now it's increasing, and then there's more CO2 being sequestered out of the air for those marine organisms. So, a lot of the models that they had were actually not entirely accurate. And so people are working at trying to improve those models. The models things like this are very difficult to model, because it's like it's not like the butterfly effect, but in some ways it's like the butterfly effect, little things here make big changes there. But anyway, H2SO3 is a bit more complicated to work with. There's another one, maybe we should try H2S. Well, H2S kind of has the same problem. H2S is normally a gas. And so when you make a solution, you have to bubble the gas in water. When you try to make an H2S solution, it's very difficult to control the concentration. So usually when people make an H2S solution, they make it saturated. They make it saturated so that all they do is they just keep bubbling H2S in there to keep it saturated, which keeps the concentration. Otherwise, if you stop bubbling it, the H2S escapes off the surface, concentration decreases in solution. The problem with bubbling H2S is it's very toxic. And the max concentration you can get for H2S in water is 0.1 molar, roughly. But sulfides are incredibly important because there are a lot of minerals that are sulfides and a lot of ores that are sulfides because sulfides are so insoluble. So sulfides are an important thing. And then there's this whole equilibrium. They're thinking about mining. Have you heard about that? They're thinking about mining the ocean floor for these minerals, like sulfide minerals, because there's H2S vents, and those will precipitate out these metals like lead and other things. Chromium, nickel, and so there are a lot of valuable minerals. But do you want them digging up the ocean floor? What's that going to release? There's probably a lot of sequestered CO2 down there and stuff. So anyway, lots of things going on. So modeling this isn't so easy, and so but people are modeling this kind of stuff. So, for example. I have one of the professors here worked at, before he retired, I think Northrop or Aerospace or one of these, and they were having a problem. He was telling me they're having a problem on the space station. On the International Space Station, they were getting precipitates in the cooling system, and they couldn't figure out what these precipitates were, but they needed to find out because this is damaging their, they have all these radiators and whatever else for heat exchange, and so it's damaging those. And so he told me they ended up using this, and we have a lab with this schedule. I forgot when that lab is, maybe next week. They use a free modeling package, and we'll be using that free modeling package. We'll be doing some modeling ourselves, I think next week or the week after. And that models this acid-base behavior as well as other things. So let's pick a different acid here. Probably we could handle this with this program. This program, by the way, is called Visual Mintech. Visual Mintech, you can just download it for your computer, and this is the type of stuff they use for the space station, so it's probably pretty good, as far as modeling goes. I mean, in other words, they probably checked because whatever model you make has to agree with experimental data, and if it doesn't agree with experimental data, you know, this experimental data is factual data, then the model needs to be adjusted. But if you have too many adjustable parameters in your model, then it's maybe not the best model. Well, anyway, getting back to this, if we had visual mentech, maybe we'll go for this. But since we don't have visual mentech, let's not go for this acid. Let's pick a different acid. And so what other acids can we pick? And there aren't a huge number on that. In fact, there's very few on that. And so let's go back to the book and we'll take a look at
Would you ever consider hydrogen peroxide or water to be dichroic acids?
in theory, yes. In practice, no. Hydrogen peroxide would make an interesting one. The problem is you're going to form oxide. It'll be impossible to see that second equivalence point. The pH would be way too high. In other words, you wouldn't be able to titrate it with sodium hydroxide. You need a stronger base, but the strongest base that can exist in water is hydroxide, so you're stuck. So it'd be monoprotic, but even as far as the pH of that, you know, it's 10 to the minus 12, that's approaching water. So its pH is going to be kind of close to water. All right, so let's pick another diprotic acid. Or a tetraprotic acid, pyrophosphoric acid. We could do hydrosulfuric acid. We could titrate that. The problem again here, and this is a tricky one. Some of you caught this, but this Ka2 is exceedingly small, worse than water. So this is less acidic than water. Water is a better acid than HS minus. Well, oxalic is a good one. Oxalic acid, they use this in Chem 1A for standardizing the sodium hydroxide solution. But in oxalic acid, when we do the standardization, we just treat this kind of as a monoprotic in a way, because we only go to the second equivalence point in the titration. So we titrate a standard, that is, we weigh out a amount of a sample, and then we titrate to the second equivalence point here. The one negative about oxalic acid is, unlike a lot of these other acids, like citric acid is generally regarded as safe. Lots of people eat lots of citric acid, and there's no problem usually with that. Or carbonic acid, no problem with that. Malonic acid. Malonic acid is used in like cosmetics and that kind of stuff. Oxalic is somewhat toxic. So, because oxalate is a good chelating agent, you know, and since oxalate's a good chelating agent, it can cause trouble in with your ion balance, electrolyte balance. What should we do? I guess oxalic then. It's simple enough. So oxalic is 10 to the minus 2. 10 to the minus 2 is pretty decent. And then 10 to the minus 5. So 5.4 times 10 to the minus 2. So we're going to do oxalic acid here. H2C2O4. And we're going to do 0.200 molar. And so if we do, let's do a 25 milliliter aliquot. Aliquot is just a portion, the solution here, 25 milliliter aliquot or 25 milliliter portion. And so where's the equivalence point going to come in?
My initial thought would be the first equivalence point would be like 12.5, but since it's 0.2 to 0.1, is that going to change it?
Yes.
Does that mean you're going to need double, so the first will be at 25?
Okay, actually the first is going to be at 50. So this is a poorly designed titration. And the second will be at 100. Yeah. It's a poorly designed titration because most burettes go up to 50. So I probably should have titrated with 0.200 molar sodium hydroxide, or if I did that, then it'd be at 25 and 50. That would be better. But that's okay. This is just some hypothetical titration. We don't have to make sure that this works on a practical level. We just need an extra big burette. And so extra big or extra large. Burette. Otherwise, this would be a hassle. All right, so we can get some points very rapidly. The first points I get are the half equivalence points because those should be pretty easy. And so the first equivalence point will have, what, the pKa1 here or the pKa2? This is going to be pKa1. And so we go back and look at the Ka1 for this. And we go to oxalic acid here, has a K1 of 5.4 times 10 to the minus 2. And so we'll just take the negative log of that. 10. 5.4 times 10 to the minus 2. Log base 10. 1.267. 1.267. What was your initial pH on your titration? Do you recall what the pH with 0 milliliters of sodium hydroxide was?
Mine was around 2.
2?
2 to 3.
If your initial pH were like 2 or 3, would you even see this? No, it's too dilute. You're going to miss it. You might catch a little bit of it. Let's say your initial pH were 2. You might see this little tail end here, which could screw things up for you. And so this is one reason I recommend that you try to get as concentrated as possible, because something that's fairly decent, I mean, oxalic acid, it's pretty high. I mean, it's a pretty low pH. I mean, it's a pretty high hydronium concentration there. So it might be tough. However, the second equivalence point shouldn't be any problem, because in the middle here, this is called buffer region 1. And so we're going to call this buffer 1. And buffer 1 forms when we do this. So if we take our oxalic acid, H2C2O4, and add our sodium hydroxide, I'm not going to put 2 sodium hydroxides here because I'm not going all the way to the second equivalence point. And then we're varying the amounts of sodium hydroxide. This is going to be the LR. This is going to be the excess reagent. And then we're going to make sodium hydrogen oxalate and water. And so when we do this, what we're going to end up, this is step 1 here. In step 2, we're going to have a mixture of weak acid and its conjugate base. And so step 2 will be the oxalic acid, sodium hydrogen oxalate, buffer. So that's what we call buffer 1. At the equivalence point, we've neutralized all of it. That is, we have a stoichiometric mixture of reactants, which is going to lead to the salt and water. And so at the equivalence point here, we just have salt and water left over. This is our step 2. At the equivalence point. But this salt is very unique because this is what we call an amphoteric salt. And amphoteric salts are difficult to deal with, and so we'll talk about that. They're difficult to deal with, but somebody's made it easier for you to deal with because they did all the math. All right, then what we're going to have is this, what we call the buffer 2 region here. And the buffer 2 is going to have a different step 1 and a step 2. The step 1 is we take the amphoteric salt, and the amphoteric salt is going to act as the acid. And then we're going to add some base to it. And so we're going to have excess acid, limiting reactant is going to be the base, and then we're going to form sodium oxalate and water. And since we have excess acid and the limiting reagents consumed, then step 2 will have the different buffer system. It's going to be the sodium hydrogen oxalate as the acid and sodium oxalate as the base. And so the pKa here, you know, at the half equivalence point, the pH is equal to pKa. And so pKa2 is equal to, let's go ahead and calculate it, would be 5.3 times 10 to the minus 5. We'll take the negative log of that. .275. 4.275. So this is 4.275. That means the equivalence point is somewhere between 1.267 and 4.275. And so this equivalence point here is not pH 7, it's pH less than 7. It's going to be a pH less than 7 for the amphoteric salt. Now that means that amphoteric salt is a better acid than it is a base. Better acid, that is the Ka, is bigger than the Kb. So we got the buffer 2 region, and then we have the second equivalence point. At the second equivalence point, we have just the salt and water, but this salt is sodium oxalate and water. This would be our step 2 here. And so we have stoichiometric mixture of acid, sodium hydrogen oxalate, and base, sodium hydroxide, and they neutralize each other out, forming just the salt and water. And this salt is a dibasic base. Dibasic. With a dibasic base, then typically we just do step 1. Step 2 is usually a minor contributor to pH, so step 1 is usually the only thing that's necessary. Actually, that step 1 would be step 3, by the way, here. If we're doing the titration from the beginning. And then here we're going to have excess base, excess sodium hydroxide, strong base region. And so we're going to have weak base, strong base. As we call this a weak, well, we should call it strong. Strong base, weak base. The pH is going to be dictated by the strong base, except right down here. Right at the edges, we have to worry about it because the concentration of the sodium hydroxide is so small. And so right at the borders here and here, we have to do ice, usually. Factor it in. This is for your step 2. Step 1, we just flipped this. And so step 1 was the sodium hydrogen oxalate plus sodium hydroxide. In this case, the sodium hydrogen oxalates are limiting reagent, sodium hydroxides are excess reagent, and we're going to form sodium oxalate and water. And so we just end up with a mixture of sodium hydroxide and sodium oxalate. So let's get some points here quickly on the curve. So I'm going to blow this up so we have some room here. So let's look at the first part of the curve here. And, from the initial to the first equivalence point. So we already determined the first equivalence point's got to come in at 50 milliliters. This is based on stoichiometry. Okay, where is this going to be here? How many milliliters? The half equivalence point. 25 milliliters. So at 25 milliliters, we're going to have what pH? pH is going to be 1.267, or pH. Give me some more points. Give me 4 more points between the initial. The initial is just the chapter 16. The initial is just oxalic acid alone. Probably just step 1's all we need for this. The weird thing's going to happen sometimes. The weird thing that's going to happen is, okay, if we look at the initial pH.
Is the pH 1.267 or is it the pKa?
The pH and the pKa are the same at the half equivalence point. And so well, let me get the Ka, 5.4 times 10 to the minus 2. The simplifying assumption might not work here because K is kind of big. But then my initial concentration is 0.200, so it's fairly large. So it might work. I don't know. Since I don't know, just give it a try and see what happens. So 5.4 times 10 to the minus 2 times 0.2. Then take the square root of that. 0.1. If I use the simplifying assumption, x comes out to 0.1. I was worried about that because this k is too big. 10 to the minus 2 is kind of big. And look at the pH that down here is so low. And so we'll have to use the quadratic, unfortunately, but it's going to be x squared plus 5.4 times 10 to the minus 2x minus 0.2. So that would be 10, 1.04, 1.08. Actually, what would that be? 0.2 times 5.4 times 10 minus 2. Times 10 to the minus 2.
1.08 times 10 to the minus 3.
Thanks. 1.08 times 10 to the minus 3 is equal to 0. All right. Now, you have to watch out for these solvers, because what happens if the solver gives you an answer like I just had it. I put it. Sometimes it gives you an answer that is clearly a round-off error, and so you have to be careful sometimes. So we had 5.4 times 10 to the minus 2, I think it was. And 1.08, and I think 1.08 times 10 to the minus 3. .0155. Now, what I mean by you have to be careful about these is this. What if x came out to 0.2? If x came out to 0.2, then it's likely something's wrong. It's likely that's because of round off. Because if it comes out to 0.2, it's going to give you 0 for oxalic acid. Or if, on the other hand, x came out to 0, if that x comes out to 0, then it's likely it was due to round off. If that happens, then you have to use something that carries more digits. So, for example, if your calculator doesn't carry enough digits, then you got to use maybe Excel. Excel carries like 99 digits. Calculate in Excel. Or you try some other trick to get your calculator to not round off. Because round off happens with the calculator, since it's a finite number of digits it carries, and it used to be only 8 digits a calculator would carry. If it's only 8 digits, then it's easy to get round off error.
I'm sorry, I think I was wrong. I think it's 1.08 times 10 to the minus 2.
Okay, times 10 to the minus 2.
Yeah.
Let me fix that. Let's fix that here. This is going to change it to 0.0803. We're only allowed 2 sig figs, so I'll just tack on 1 extra digit here. And then it goes beyond the number of decimal places here. And so this is going to come out to... the reason I'm going to, the reason I don't have to do these, because all I'm interested in is pH, And if I assume step 2 is negligible, then I'll just stop here because this is my hydronium. But the reason I'm going to do this is because I want to do what? The reason I'm doing this is so I can check my numbers, you know. Because normally what we do is we check the back of the book for the answer, right? But what happens when we can't check the back of the book for the answer? Well, we have to figure out other ways we can check if the answer is correct or not. And so what I'm going to do is I'll just do 0.0803, square that, divided by 1797. And see what my calculated K comes out to. My calculated K comes out to 4.46 times 10 to the negative 1. That's my calculated K, and then I compare it with the K, the actual K. The actual K is 5.4 times 10 to the minus 2. So that's indicating that maybe I made a mistake somewhere. It just doesn't seem close. This is a bit more than round-off error here. So I try to figure out what might have went wrong. So let me redo my calculations here. So 0.2 minus 0.0803. Oh, I see my mistake. My mistake, I put 1797. It's not 1797, it's 1197. Let me try that and see if that fixes this. So let me invert this times 0.0803 squared. Yeah. Now I get 5.38 times 10 to the minus 2. And it's supposed to be 5.4 times 10 to the minus 2, so it's good. And so I recommend doing this, you know, as a quick check to see if your calculation, then you can see quickly that if there's a mistake, you can try to go back and fix it, if you aren't already doing this. It's a good thing to do. All right, here I would take a look at Ka2 next. And when we look at Ka2 for oxalic acid, it's 3 orders of magnitude smaller. So we're going from 10 to the minus 2 to 10 to the minus 5. We expect negligible additional hydronium here. There should be nothing. And so I'd stop here. And I'm going to calculate the pH based on just step 1 being the major contributor of hydronium. And so we'll just do that. And the thing is, that comes from experience. So you're lacking experience, so the best thing to do is just do the calculation, although it does take time. Do it and see, you know, what it comes out to. And so that was it was, I think, problem number 97. That's it. And so the pH comes out to 1.095. That's really low. Oxalic acid is borderline strong. Now, if you look at the chart here, where is oxalic acid? Oxalic acid is borderline strong, even though its K is only 10 to the minus 2, so you're thinking it's got a small K. But, you know, if it were a strong acid, its pH would be around 1, you know, regardless. And so the initial pH here is 1.095 or 1.10. We'll just go with 1.10 pH. And then it climbs up to 1.27 here at the halfway point here. Okay, there are 4 more points that are really easy to get here. Actually, 2 more that are super easy to get. You know what those are?
So
Yes. Let's go to the 1/11th. What's the pH of the 1/11th equivalence point?
I forgot.
PKA plus log 110.
Well, at the 1/11th, it's a pKa minus
It's gonna be minus one.
-1. And so it's 1.1. If this is 1.27, this will be 0.27. Can we get that low of a pH? No, not at this concentration, we're not. And so this is why oxalic acid is a bit weird, because our calculated pH is, it can't be. We can't have a starting pH of 1.1 and add strong base and expect this to drop down to 0.267. That's impossible. We're adding strong base, the pH can only go up. And so this is an impossible pH to get. Just like the reason in the titration for the triprotic acid, phosphoric acid, we don't see the third equivalence point. That's an impossible equivalence point to get to, because even though we calculate it, we're not going to get there. It's too high of a pH for our base. This is too low of a pH. We aren't starting that low. And so let me put a little asterisk there. But we will see the 10/11ths. What will the 10/11ths come in at?
2.2.
Yeah. So at 2.2, I'm just going to round it. At 2.27, we're at the 10/11ths. Now, where is the 10/11ths in milliliters? It's 10/11ths of, well, of 50. So what is 10/11ths of 50? So we'll have to calculate that. So take 10/11ths times 50.
45.45.
Okay. So it's not at the cleanest, but at 45.45, we expect a pH of, yeah. And this one we should be able to observe. Let's get 2 more points so that we can kind of see how the curve, is. And so what are 2 more points that we can get? That should be pretty quick. The 1/4. The 1/4 is going to be at how many milliliters? Yeah, 12.5. And the pH will be the pKa plus. Did you memorize it? If you didn't, then we could easily figure it out, because the pH is equal to pKa plus the log, and we've neutralized 1/4, so we're at the 1/4 equivalence point. How much is left over? If we neutralize 1/4 of our acid, then we still have to neutralize an additional 3/4. The quarters cancel, and that leaves you with log of, and log of 1/3 is, and so let's do that. Log of 1/3 is, I'm gonna just do this to do decimal places. Maybe it's easier to memorize. I do it to 3 decimal places. It's pKa minus 0.477. So 1.267 minus 0.477. It's too low. This is 0.78. And so we're going to put a little asterisk there. We're not going to see that one. That's too low. However, we should see the 3/4. Now, the 3/4 equivalence point is going to come in at how many milliliters?
37.
Yeah, 37.5. And this will be 3/4 on top, 1/4 on the bottom. And so it'll just change the sign of this. So it'll be plus 0.477. So 1.267 plus 0.477 0.477 gives me 1.744. And then I rounded at the end, and so this will round to 1.74. I've rounded this one already. And so we kind of can see it's going to go up to 1.267, 1.7, 2.27, and then we hit the equivalence point. And so let's calculate what the pH is at the equivalence point here, the first equivalence point. So in the buffer region, we don't have to do step I, step 1, step 2. However, once we get to the first equivalence point, then we have to revert back because we're no longer in the buffer region. And so when we go to the first equivalence point, we're going to have plus 50.0 milliliters of sodium hydroxide solution. And then we had our 25.0 milliliters of oxalic acid. Oxalic acid, I don't want to write it over and over again, so I'm going to call it H2OX for ox acid. Now the concentrations are different. The oxalic acid was 0.200 molar, and the sodium hydroxide was 0.100 molar. And so we're going to do our solution dilution first. This is going to give us 75.0 milliliters of mixture, reaction mixture. In this reaction mixture, I need to calculate my new concentration of oxalic acid, H2OX. And I have to factor in the dilution factor. So the dilution factor here is going to be at 25.0 to 75.0. That's our initial over the final times the initial concentration, 0.200 molar. And so this is going to be 1/3 of that. So let's see what that comes out to. All right, this comes out all 6s, so I have 3 sig figs. I'm going to carry 1 extra. Just keep track of sig figs this way. So quadruple 6. I don't round here because that's going to screw things up when I do the next step. Okay, this is going to be a 50 to 75 dilution of 0.100 now. 2/3. Actually, what does it come out to?
Shouldn't it be the same?
Yeah, it comes out to the same. You're right. Well, actually, it's supposed to come out the same because this is the stoichiometric equivalence point. So we should have stoichiometric ratio, which is a 1-to-1. That's where it comes from, equal amounts. In this case, equal concentration. So let's go on to the next step. We'll take our oxalic acid plus our sodium hydroxide. And this is going to make sodium oxalate and water. Actually, it doesn't make sodium oxalate. It makes sodium hydrogen oxalate, sorry, and water. I need to fix that. All right, so initial change, equilibrium. This is going to be 0.0 quadruple 6. 0.0 quadruple 6. 0, and water is pure liquid. And so by the time we hit the end, K for this is very, very large. And So it should go to completion. Strong reacts to completion, sodium hydroxide. And we end up with 0.0 quadruple 6 molar sodium hydrogen oxalate. Now we have a problem here for the next step, step 2. The problem here is, which should we do? Should we do Ka for hydrogen oxalate? The Ka for hydrogen oxalate, we can just get off the chart there, or off our books chart.
I understand that it's, it's a very strong acid, but why didn't you use very large instead of the 5.9 instead of negative?
The 5.4, is it 5.9 up there? Yeah. Yeah, that data is a little bit older, so we're going to use our books data, which is 5.4 here. And then hydrogen oxalate up there is 6.4 times 10 to the minus 5, and here it's 5.3 times 10 to the minus 5, so we'll use this books data too. But the reason, let me go back to your question. The reason is because it's a different reaction. So the reaction here.
Oh, I think I got it. Is it because the K is for when it's with water and
Yes.
this is with
Right.
sodium hydroxide?
Right.
Okay.
So if we take oxalic acid and react it with water, then it's 5.4 times 10 to the minus whatever 2. Water is a weak base, terribly weak, but sodium hydroxide is a very strong base, and so this is going to be much more favorable, and so that's why I called it very, very large.
So is it going to be very, very large with all weak acids, and if it's combined with sodium hydroxide?
Yeah.
Strong acid?
Right. Right. My system is this. If it's a strong acid with a strong base, triple V, very, very, very large. If one is strong, the other's weak, then it's double V. If one is strong and the other is water, then just 1V.
Okay.
That's the ranking system. So the Ka for hydrogen oxalate, we can look up on the chart, 5.3 times 10 to the minus 5. So what this is hydrogen oxalate collides with water. In this collision, water takes the proton, and we end up with oxalate and hydronium. So oxalic acid loses the proton. But hydrogen oxalate is amphoteric. And so hydrogen oxalate can act as a base. And so we'll have a Kb for this. This is the same species. So it's the Ka for hydrogen oxalate, the Kb. These aren't conjugates. They're the exact same. When we have a conjugate, one's the acid, and then we have its conjugate base, which is difference. But what is the Kb? The Kb we have to calculate. So this is going to be 1.0 times 10 to the minus 14 Kw divided by the Ka. It's going to be the Ka for what? Ka for hydrogen oxalate, or the Ka for the conjugate acid of hydrogen oxalate? Yeah, it's going to be oxalic acid. So this is going to be the Ka for oxalic acid, which was 5.4 times 10 to the minus 2. So I get 1 times 10 to the minus 14 divided by 5.4 times 10 to the minus 2. And this comes out to, let's see if you got the same, 1.85 times 10 to the minus, times 10 to the minus 13. Is that what you got? Now does this describe the same equilibrium? And so let's take a look. The KB equation will be HC2O4 minus plus water. The only difference here is, in this case, water takes the proton off hydrogen oxalate. Over here, hydrogen oxalate will take the proton off water. And so we end up with is oxalic acid, conjugate acid plus hydroxide. Do these describe the same equilibria, or are they different? They're different equilibria here, because over here, this is describing the equilibrium between hydrogen oxalate and oxalate. Over here, this is describing the equilibrium between hydrogen oxalate ion and oxalic acid. So these two are not the same. They're different. And therefore, we have to consider both of these. Now, which one should we do? Should we do Ka first, followed by Kb? Or should we do Kb first, followed by Ka? Which one would you lean towards doing first, if we have to consider both of them because they're different? They're different, but they're related. They're related because they both contain hydrogen oxalate. But they're different because one goes to oxalate, the other goes to oxalic acid.
Isn't the KB equivalent to the one we just did, the NaOH?
Yeah, this Kb is extremely small. So what we might do is we might just do Ka and ignore Kb. If we did that, then we'll be close, because this Kb is close to water, 10 to the minus 14. And so we might be close. But in general, this is a special circumstance. In general, when we have an amphoteric, we have to do this. Just say this. One's going to produce hydronium, the other is going to be producing hydroxide. These are related by Kw. Kw ties these two together. And so the answer to this is you have to do this simultaneous. Ka, Kb, and Kw. That's the answer. Now, the simultaneous that we did was only two, like Ka and Kw, or Kb and Kw. We never did three, right? But the thing that makes this a lot easier is it's the same species. And so after doing all the algebra, let me just finish right here. After doing all the algebra, we come up with a very simple equation. pH is equal to the pKa of the ampho plus the pKa of the conjugate acid divided by 2. Is that a simple equation or what? That is a simple equation. But it only works in the special circumstance where the acid and the base are the exact same species. It only works if the acid here and the base are exactly the same. And then the simultaneous simplifies into this. So you do all the work here, and we end up with this. So amphoterics are actually hard if you solve it, simultaneous, but easy if you just make some assumptions and just use this engineering equation at the end. So I'll stop here. We're out of time. Then Yeah, there's some chocolate there, Halloween chocolate.